Okay, so everybody,
Yep.
welcome back, and let's welcome Sylvia. Thank you for joining us. We're very happy to have you, and let me also thank Massimiliano, who also just joined, who will be acting as a panelist or informal discussant. Rules of the game are always the same. If you have clarification questions, just come along and unmute. Otherwise, you can wait for the Q&A at the end when we stop the recording. And Sylvia, floor is yours, and looking forward.
Yes, so thank you very much, Michele, for the introduction, and thank you to the organizers to invite me to this seminar. I just said I was not that aware of that great seminar series, and for sure I will join now every now and then that I know that you have so, of course, other than me, such great presenters, basically. Today I present the work, joint work with Rodney Strong from the University of Queensland in Brisbane. And you see the title, it's called Dynamic Factor Models with Common Drifting Stochastic Trends. And I'm presenting, maybe a couple of participants have seen the paper at some conferences, workshops. So the first part will maybe be a repetition, but I plan also to include some extensions that we have been working on to address some comments that we have obtained concerning the work. So let me first motivate what this is about and motivate it with data. So 2 slides of data here, where you see the first data set on which we have an application in the paper. It's a set of series, yearly data series, GDP, real GDP per capita, spanning the period 1960 to 2019, well known, taken from the Penn World Table. And if you look at those series in levels here, they are ordered by their end, basically end value. And it ends in 2019 because there hasn't been a new release of data since I first downloaded the time series. But of course, we would expand it if there would be a new release. And looking at the levels of these country of these data, you may wonder whether some countries would grow or shrink, maybe because some countries are shrunk over this time period. Which countries grow basically at the same rate, and maybe if some countries, a group of countries, basically started at the lower level, whether they would catch up at some point in time, so whether some groups grow faster than others. So this is one motivation for looking, of course, at the factor model. And if you look at the levels of the series, to keep the trend of the series in the factor model. So that's why we're talking about common trends in time series. A second data set is much more challenging. I received it from Maya In and Paul Gagel. So it's a bunch of time series about relative capital goods in of the United States. So this sample period spans the period 1982 to 2018. And basically, we have 2 broad classes in here. So ICT and non-ICT prices, and subcategories like equipment and structures. So capital goods prices related to the residential sector, non-residential sector, consumer and consumer durables, basically. And if you look at those if you look at those time series, on the left-hand side, you have the full cross-section, and you see that those time series in pink that I highlighted here in pink basically started at a relative very high level and decreased over time. So they had a large negative growth rate. So basically, those time series, so there are a couple of time series that decreased by basically 99%. Zoom in on the right-hand side, you see those time series that are more packed. So, and you see that there are various, again, some time series show a decrease in their relative prices, and some time series show an increase in relative prices. And you see that, I guess that's in 2010, sorry, they have been normalized to 1. And if you want to analyze those time series in levels, so that seems quite challenging, but we are able to basically to capture common drift, so groups of time series that display a common drift. And the economic question that is that basically is in the background of such an analysis, of deriving a model to analyze this, is basically, it was a question raised by Maya and Paul, in fact. They wanted to know which prices so would be driven by the same technological process, because basically what we have in mind is that the technological process, if it diffuses differently to various sectors, has a different influence on relative prices, basically. And so being able to extract prices that are driven by the same process enables afterwards also to build, let's say, a sensible aggregate of those, an aggregate relative price level of those individual price series that you can further use, maybe in a macroeconomic model, etc. So that's why we have a second application on those data series. Now let's come to the econometric motivation. Basically, in factor models, usually you don't include the drift. You don't model the drift. So I say usually there are some papers who allow for trends, let's say. I will come to the literature afterwards. But usually data are adjusted to be non-trending, basically. So this means you mean adjust data. So the YIT, basically the growth rate, is mean adjusted by Y bar I here. And series normally are also standardized. And then if you have a large cross section, you build up a factor model. And you see it in those 3 equations for the factors. I include here an AR1 process. Of course, in the applications, you could also have more than just 1 lag. So I keep 1 lag here for expositional convenience. We also allow normally for dynamic processes or AR processes in the idiosyncratic components here. And in this setup, basically modeling the demeaned and standardized time series, the factors that you extract, they capture the joint dynamics. That's usually what people are interested in. So if you think of the many applications, we look at the business cycle dynamics. And that's the motivation. So we don't look at drift, but the factor that you extract here, it would contain the stochastic part of the trend component, but not the drift. And so the stochastic part of the trend component would be the sum of the shocks. But as I said, without incorporating the deterministic component, so the drift, the drift that might be present in the same drift that might be present in a group of time series. And basically, so the motivation is that I have it on the second next slide, to put back the drift in this factor equation, to extract factors that reflect the common drift of time series in levels. Literature that has really explicitly modeling, I highlight here in blue A drift, and I will justify this highlighting here, is in my view quite scarce. The oldest one that I recall stems from Stock and Watson back in 1989. They extracted coincident and leading indicators from, let's say, a small panel set, basically. And a couple of years later, Kim and Nelson revisited those time series, and they extracted also a drift from the Kaufmann gain. Basically, they estimated the same factor model, but including a Markov switching drift in the factor equation. The drift, so in those two papers, the authors extract one factor, and the drift is identified by looking at the Kaufmann gain. So basically, they identify one factor and one drift to then compile basically the level of the coincident and leading indicators. It's only so let's jump to Müller, Stock and Watson. So that's the most recent paper that I read very closely, where they extract also from the Penworld data set, from an expanded data set, basically one long run factor, so the common factor that drives those data, and they model the low frequency components of GDP. So they apply a factor model to basically to extracted long run trends in the time series. And the common factor they identify is basically calibrated to closely follow basically the drift or the level of developed countries, of the OECD countries. They also extract one drift, so they are interested in extracting the drift because they make long-run projections. And this is clear why. So if you make very long-run projections, so several hundred years, then you can use this for any long-run projections, like, I don't know, if you do the analysis for climate change, etc. So this is very useful. They have also group components, so factors that capture long-run features in groups of countries, which don't include the drift, however. So these group factors, basically, they are there to model, let's say, they slowly mean revert in the very, very long run then to this common long run factor. There are other papers like the paper by Bai and Eng, and here, which include series-specific, so deterministic terms, but they model explicitly series-specific trends. So they don't assign the trend to factors. They simply estimate series-specific trends, and then for the analysis, they remove those to the analysis of the factor. And then there is a recent group of papers. I just list here two of them. By Barigozzi and Luciani and Antolin Diaz and co-authors here, which model via factor models targeted variables. And we see what variables they target. So Barigozzi and Luciani, they target the output gap. And so basically an unobserved variable. So they want to have a good measure, let's say a real-time measure of the output gap. And it's clear to measure the current state of the economic stance. And Antolin Diaz and co-authors, they are interested in having a good real-time forecast for GDP growth. In both papers, so Barigozzi and Luciani, they extract multiple factors. Antolin-Diaz extract one factor of a specific group of variables. So the variables that they include in their factor model is really targeted to a good, let's say, measuring or good forecasting performance. They model time-varying drifts explicitly, but again, targeted drifts. So in Barigozzi and Luciani, they model time-varying drifts in GDP growth. So, and Antolin-Diaz and co-authors, they model a time-varying drifts in two specific variables, so in GDP growth and consumption growth. And for the rest of the variables, they assume a series-specific constant growth rate. So it's in those papers are quite related to what we are doing, but basically they don't include the drift in the factors. So they don't. It's not the factors that include the drift. So it's the drifts are targeted towards specific series in their data set. I will come back to this a bit later on. So what is the contribution of our paper here? It's basically that we want to include the drifts, to assign the drifts explicitly to the factors. And we also model basically factors, so more than one factors. We extract as many factors as are present in the data set. And as I highlight here, we want to explicitly assign the drifts again to each factor that enters the model. And it's clear if the drifts in the factor do not account for the whole drift that is present in the time series that we observe in the time series, the rest will enter the idiosyncratic component. So this delta I will just be the remaining, basically, of the trends, the deterministic drift that we observe in the time series that cannot well be explained by the factor. It's a data-driven inference. I will not go too much into let's say the model estimation. I will focus on this on the approach to assign, basically to decompose the series-specific drifts into factor drifts and assigning the remaining to the idiosyncratic component. But basically the method and the estimation approach we pursue here is data-driven. First, to identify the factor space, we will induce shrinkage into the factor loading matrix here into this lambda ik. So that's the loading of the factor k on series I here. So this defines, these elements define a potentially large matrix. And by inducing shrinkage into this factor loading matrix, we extract factors that load on various groups of variables. So those time series that are driven by the same factor will have loadings shifted away from zero, and those not really affected by some factors, those loadings will be shrunk towards zeros. And so we hope, at least that's our experience so far with the data set, is that the factor loadings in the columns of this factor loading matrix will define or name the factors. So we can give an interpretation to the factors. And of course, there might be some rows with zero loadings. So sometimes series might not be affected by factors. So they show completely idiosyncratic behaviors, and those loadings will be shrunk towards zeros. And in that sense, we also obtain a very precise estimate, or let's say a more precise estimate of the factors. So not only interpretation, but also more precision in factor in extracted factors. Rotational identification. So when estimating the model, we don't care about the ordering of factors. So we will have label switching. So in factor order, here. And the factor order will be identified by post-processing the posterior output. So we pursue a Bayesian approach, and at the end, we collect all our draws from the posterior distribution, and we reorder those draws to obtain an identified, let's say, factor model, which identifies the factor order, basically. And yes, and we obtain a sorted output by this post-processing procedure. And the focus, basically, of this presentation will be to present you or to show you how we decompose series-specific drifts into factor drifts and the rest, basically, in these idiosyncratic drifts. And this decomposition is based on a statistical model. And this statistical model will provide us a mean for this drift decomposition. So let's start out from what we call the reduced form non-centered specification here of the factor model. So again, so what we do, so for the two data sets that I showed you at the beginning, we simply standardize those data sets. Okay, so the standard deviation is computed on growth rates. I'm sorry, I shouldn't have had here another variable here, not YT. So it's not the standard deviation on the level, it's the standard deviation on the growth rate, and we standardize the level by the level of the time series. And we model the growth rate of this. No, actually, it's right. The growth rate is it's simply standardized. It is not demeaned. Okay, so the notation is okay here. And you see what is observed from the data is basically the series-specific growth rate. So what I can estimate if I condition on the factors. So if I know the factors, I could simply estimate this equation by a linear regression and obtain an estimate for the series-specific growth rate. Ci here is the constant or the intercept on this equation for the growth rate of the time series, and I would obtain an estimate for the factor lengths. Under the shrinkage prior, the posterior will show a will also come basically from or basically the posterior will show for some loadings a strong concentration at 0, for other loadings that they will be shifted away from 0. So we call it reduced form because the series-specific growth rate here does not provide a mean to decompose the series-specific growth rate into factors and idiosyncratic components. And basically, we call it non-centered because in this representation, the factors here, the F star, the factors and also the idiosyncratic component has been adjusted basically by their unconditional growth rate. And that's what is illustrated in the last two equations here. So the factor that I had previously here on this slide, let's say in the centered version, so the factor was centered on the conditional growth rate here, is adjusted for the unconditional growth rate on this slide here. So mu k star is the unconditional growth rate. And once I can demean, or let's basically, demean the factors by their unconditional growth rate, I get this non-centered factors which are not centered around their unconditional growth rate. So that's why we call this representation the non-centered specification, because here the F star is not centered around its mean. So it is a demeaned version of the centered. So how do we come from this specification, which where basically the growth rate is identified, so I can estimate it by linear regression, to the decomposition of the CI here into a part that is driven by the factor, and the rest is assigned by the idiosyncratic. So now I would like to motivate this statistical model, how we to decompose this series specific growth rate, the CI star. So once I have an estimate for CI star and F and lambda here, so conditional on FT star, then I can specify a model to extract factor drift. And I have various possibilities here. So the target is to decompose this CI star into a part for each time series, basically, into a part which is factor driven. So the factors would have a factor drift, basically, and you see the UI here. So what I allow for here is basically that the factor specific drift for each time series could slightly differ from the fact, let's say the average factor drift or factor drift. And the rest, the part which is not driven by the factor is assigned to the idiosyncratic. So if I condition on lambda I, and I have an estimate also of CI from this regression analysis, I can specify a statistical model to obtain this decomposition that I'm interested in. And the statistical model, so I know the CI star. I also have an estimate for lambda I. And now you see that I can set up basically a mean decomposition statistical model. This lambda I mu tilde I star, we call it the series-specific factor-driven drift component. And you see why, as I said, so the factor-driven drift for each time series can slightly depart from the factor drift that we extract. And the statistical model that we have in mind here, so is that this mu I tilde is normally distributed with a mean of mu star and variance, so U, let's say heterogeneity across the I's. And for mu star, I also have a prior specification, so a normal prior specification with mean mu m star, capital M star as a and U, these random drift deviances, which we allow for each time series, this U is diagonal. So we have independent factor equations here. And so also the drift deviances heterogeneity is independent across factor drifts here. And for each element, we specify an inverse gamma prior. So the point here that I want to make is that the drift deviance that we allow for here will be estimated. So whether it's relevant or not will be indicated by this U that we learn from the data. If it's close to zero, okay, if U or one element of U is close to zero, then basically we're back to a pooling model. So the model would be that the mu I tilde would be equal to mu star and would not randomly deviate from mu star. So this specification, it's a random effect specification. Okay, that's the analogy. And we call it the random drift deviance that we allow for each time series. So each time series factor-driven drift deviates randomly from the factor drift. And what is the motivation? So basically, if I condition on Ci and lambda I, and I have this statistical model with prior specifications, I can perform a posterior update of mu star. So I obtain a scaling of the factor drift based on these parameters that I have estimated from this regression setup. What is the rationale for allowing these random deviances here? You can, so first you remember the data sets that I showed you. So for the real GDP per capita time series, it doesn't seem obvious if we have group of countries that display the same drifts that there should be a large deviance across the factor-driven drifts. For the capital price series, recall the graph I showed you, all time series or each time series nearly follows has a different drift. And then random deviance from a factor drift is more obvious. And the economic rationale basically for these random drift deviances is motivated here. I just only list a couple of motivations here. So maybe economic, so basically wide processes. So if we think of technological processes driving those time series, they affect either countries or units for specific countries in a different way. And this might be due to differences, as I motivated, different sector-specific technological diffusions, different capital labor ratios, across sectors or also across countries. Across countries, you observe different market structure or different human and physical capital accumulation. And so even if countries display the same drifts, they can randomly deviate, and the drift would be basically driven by a factor, a common factor. The series-specific drift or the country-specific drift could basically deviate a bit from the factor. And here I just show you that the update that we obtain for the factor drift, so basically this mu star, if I do the posterior update, I have listed here the moments, so I get a variance, and for the mean, I want to highlight here because why the scaling of the factor drift is in a sense data-driven. You see that the posterior mean for the factor drifts that we extract is an average, of course, of series-specific drifts. So C star includes all the CIs here. And you see that the weights that we attach to the C star, so the M plus lambda prime E in capital E inverse here, the lambda prime here shows you that the factor drift is a weighted average of series-specific drifts. Okay, this is basically in a simple average. We would simply average over series-specific drifts. So build the sum and divide by n. And here we build the sum, but the weighted sum, weighted by lambdas, by the factor loadings. And so those time series which are strongly loaded by a factor, where the factor loading is large, they obtain a higher weight when determining the factor drift. And those time series which are not heavily loaded, so they have a factor loading that is shrunk towards zero, they obtain a zero weight or a very small weight when this mean is computed for the factor drift. And so that's how we obtain basically a scaling for the factor drift. So the factor drift will be determined by the series-specific drifts, by those time series which are strongly affected by the factor. So that's in a nutshell what we are doing methodologically. Yeah, to extract the factor drifts and to scale them, basically. And with the scaled factor drift, so once I have this mu star, of course I can draw from the posterior distribution a specific value. I can recenter factors. So if I add this mu star to ft star, I rescale basically, or sorry, I recenter the factors, and then I can return to the centered specification. Centered specification where YIT is determined by factors. The factors are centered around their drifts, here around the conditional drifts again. And you see that here the idiosyncratic component basically has two components here. First, the idiosyncratic part, so basically including the drift, the remaining drift that is not determined by the factor. And because we have this random drift deviance, so basically I show you here the marginal model where the idiosyncratic term also picks up this random drift deviance. So this lambda I times ui star. So basically, which is basically I assign it here to the idiosyncratic part, but also this part contains a part coming from the factor, which is factor driven here, and the remaining, basically the, let's say the genuine idiosyncratic. And the rest of the parameters, so the parameters determining the factor dynamics, so also mu k, the parameters determining the idiosyncratic dynamics are estimated or sampled from this representation. As I said, so in terms, I just want to check. Yes, I will hurry up a bit here because I will want to show you these extensions. So I don't know, are there some questions so far? Just to ask. Otherwise, just okay. So the Bayesian approach, so the sampling scheme that we derive here is a very basic one. We have very standard so prior specifications here. So the distributions that we assume, you see now here they are in this calligraphic letters here are normal inverse gamma distribution, so nothing fancy here. And this normal gamma distribution for the factor loadings, which induces this shrinkage of into the factor loading. You see that in fact also for the delta I, so the drift in the idiosyncratic term, we induce a shrinkage. So we assume a normal gamma distribution here because this reflects basically our expectation or basically our prior that we want to assign as much drift of the time series as possible to the factor. And so if the idiosyncratic drift is not really there, then basically this delta I is shrunk towards it. As I said, the sample is also very standard. So we sample, basically we have two steps. We sample the factors conditional on the parameters, and then we sample the parameters conditional on the factors, where basically the specific part for sampling the parameter is this parameter expansion set, as that I just explained you intuitively. So to sample the factor loadings, we move into these non-centered specifications where factors are non-centered. We obtain an estimate of lambda and c, and then conditional on lambda and c, we can obtain an update for the scale mu star. And then we recenter factors and simulate the rest of the parameters on this centered specification. Here, this is just for, let's say, in more details, how this parameter expansion step works. So to enter this non-centered representation here, up here you have it in more details how this CI relates to the underlying model parameters and the factor driven drifts and the idiosyncratic drift. So here, to enter this non-centered specification, we need a draw for mu star, basically, because we want to mean adjust the factors, and we simulate a mu star from a so-called working prior. So we can, conditional on factors, we obtain a working prior from mu star, we draw mu star, and we can adjust factors. And the prior induced for CI, conditional on lambda, basically conditional on psi I and delta I and mu star and mu I star, is derived from the prior of lambda I. And as I said, we can update lambda I and mu star, and then we get the scaling of mu star. And by rescaling the factors, we continue in the centered specification. Yes, so here is a picture, again, to just show you what happens. So this is at some iteration m. After convergence, we get this working prior for mu star in black here. We draw from this prior a mu star, adjust the factors. So in the black line would be the current draw of the centered factor. We adjust the factor draw to the broken line. So this one is uncentered, or basically centered at 0. We update lambda I and obtain a scaling of the factors. So in red, you would see the posterior update for the factor scale. We draw a value from there, the red mu star, and readjust, recenter the factor draw. And you see that basically here in the shaded area shows you the 60% HPDI for the factor. You see that basically both draws, the black one and also the red one, they lie within the area of high posterior density here. So this illustrates basically this step that we're using here to obtain a scaling of the factor drifts. And basically it also illustrates you that this parameter expansion introduces additional random error or in the sampler. And this helps in basically decorrelating the draws of the factor loadings and the factors. Normally they would be highly correlated. You would have a high autocorrelation in your MC draws. And this parameter expansion also helps in decorrelating, so in introducing additional random error simulation. Okay, what can you do once you have the estimate? So we have a very simple application in the paper. So now that we have factors which include the drift, of course, we can estimate the factor, the level of the factors, so the trend level. And we use here the well-known Beveridge-Nelson decomposition, which relates basically the growth rate of a time series to its level, driven by the stochastic shocks. So the level of the factor will be the sum of all past shocks and plus mu times the deterministic, mu times t, the deterministic drift here. And for each time series, we can obtain the decomposition into a trend level, the trend component driven by the factor, and the trend component driven by the idiosyncratic component. Because of course, the idiosyncratic component also includes this the drift delta I. If this is not really shrunk to 0, the idiosyncratic component usually it's non-trending. So really the trending behavior is assigned to the factor if the series is loaded by the factor. But it's allowed to be non-stationary. Okay? And so we also have basically an idiosyncratic trend component here for each time series. A simple application. So let's see what is the result for the two applications that we have here. Maybe I will just show quickly basically the application. So the drift, the trends, sorry, the factor trends for the capital prices that we are able to extract. We are able to extract 4 factors. And you see here two groups that show a very large decrease in the prices. So over the sample period, in particular since the mid-90s here, and two groups apparently that show an increase of relative prices over time. One shows quite a typical pattern. We see here a sharp increase before 2000 or up to 2008. And then a sharp drop afterwards in 2009. And this is clearly related to the great financial crisis that we observed. Prices of this group of series basically recovered afterwards. And here, the second group, so factor 1 here, also shows that increase in the front of the before the financial crisis, and then basically they remained at the same. In terms of drift deviances, remember that the U, so the amount of heterogeneity needed to model a series, the deviation of the series-specific drifts from the factor drift is not that large for factor 1, 2, and 3. You see that U is very small, so the heterogeneity across the mu tildes is not that large. For the second factor, however, you see the uncertainty is also very large. You see a larger heterogeneity here. And so we can infer from the data where the heterogeneity is important and where not. For the 4 factors, we can attach basically an interpretation. So recall the 4th factor and the 3rd factor, the 4th factor. So let's see, the 4th factor was the one with the build-up for the financial crisis. And you see that basically it loads on capital prices related to structures. So basically to buildings. Non-residential and residential buildings. So basically, these are capital goods prices related, for instance, to ceilings of apartments or floors of apartments or firm buildings. And the same for the other 2 factors. So basically, factor 2 and 3 here, they load on ICT components, you see, and also equipment. And it's clear that ICT components, the relative price of ICT components has obviously declined very strongly. We obtain a good fit of the data. For the capital goods price, for the GDP, real GDP per capita time series, we obtain 2 factors. Here you see again the median trend factors for these 2 groups. And if we have a look at the loadings, so clearly factor 1, if we look at the non-zero loadings, let's say, the first factor mainly loads on developed countries, and the second factor mainly loads on developing emerging market economies. So in that sense, the factor model is able to basically extract 2 distinct drifting behaviors. So I just want to point out now in the rest of the minutes that the rest of the time that is left here, that this approach is quite general. You might say, okay, we had yearly data, which obviously show very persistent drifts. How about other data sets? And basically, those additions are based on comments of referees that we obtained, and working on them has been quite hard. I have to say, I had to think about quite hard about them. But actually, they demonstrate that this approach is very general. So we demonstrate by using other data sets, for instance, on sectoral employment, which was used by in his publication of Journal Econometrics, that the factors in fact also are able to extract outliers, which of course you could model explicitly and remove from the data series beforehand, before you estimate the model. They are also able to capture crisis periods, like strong movements during the financial crisis and the recent COVID pandemic. We estimate also the model tool for the FRED QD data set. And the specific feature of this data set is that it's quarterly data, so you have a lot of business cycle frequency in there. And obviously, some time series enter in levels. And it's clear, so the factor models, even if it includes a drift, if factors load mainly on series entering in levels, the drift then simply represents the mean level of those time series. And of course, the application that we had determining the trend component in those time series doesn't make sense. So then you have to adjust basically your the purpose of the application, or let's say the posterior posterior evaluations that you are doing with this model estimate. Nevertheless, we are able to extract 7 factors. 2 of them load actually on series entering levels, and we have 36 series entering levels. It's a bit more than the transformation suggested by McCracken and Eng. And we, again, so what I want to show you is that the trend level of the factors, which load mainly on first difference and basically the first difference of the log of some time series, they reflect economically interpretable features, and which are so like the financial and COVID crisis, inflation surge, or jobless recoveries. We also extend the model specification to time-varying drifts, because I referred to those 2 papers which model time-varying drifts to well measure the output gap or obtain a good forecast for GDP growth. And basically, we allow for time-varying drifts in each factor equation. We are able to, so we've specified this in a way to again assess whether time variation is important or not, so we perform inference on it. For the 2 data sets that we analyze, there is not much time variation, let's say in the level, in the mu k, but once you compute the compounded drift, let's say which is similar to the unconditional drift in the constant specification, then you see a bit more time variation. And in fact, you can also use the approach, even if you want to include stochastic volatility, have a different lag structure on loadings, etc. So the basic approach goes through. Okay, this parameter expansion step, once you condition on the factors, the thing you need is to obtain an estimate, or let's say a working draw on the unconditional growth rate of factors, and then you can go to this non-centered representation and obtain a rescaling of the factors. So let me just only show you this via the estimate for the FRED QD data set. So here again, this circus graph, where you see that the chord from each factor tells you or illustrates you on which variable and on which group basically it mainly loads here. So we have the various groups here in this arranged in the circle. So national income account variables, then industrial production, employment, housing, here are prices, interest rates, productivity, money and credit, and then other financial variables here. You have the main factor, which is related to production, basically also related to business cycle conditions. Here, loading on many variables, so that's the pervasive factor, the real factor that you usually extract from the data. You have, I name it here simply production 2, because in fact that's a factor that also loads on quite a large group of time series, and basically it captures additional features related to the financial crisis and the COVID crisis. The two factors loading on the levels are here, so it's called term premium. This would be the spread or term premium factor and the interest rate factor. So those two factors, factor 3 and 7, mainly load on variables entering in levels. And we have a factor affecting prices here. You see the purple or the dark pink color relating to the prices. If we look at the level, trend level of the factors we extract, so you see in red, this is the productive production factor, or let's say business cycle, this real factor that we extract. And that's the blue one is factor 1. And that's what I told you. So we are able, so this factor 3 reflects the the financial crisis, and the blue factor captures the additional dip, maybe in some sectors or some variables related to some sectors during that period. And in the COVID crisis here, you see the real factor also plummeting here. And basically the factor 1 also related to a lot of variables. Somehow this factor captures the pickup after basically the COVID crisis. The yellow one is the price, the factor related to prices. And you see that after the long, stable period of stable prices, you see clearly the inflation surge in prices. And down here, the green factor is the employment factor. So basically, and it reflects kind of what has been termed the term of jobless recoveries. You see that after the financial crisis, employment decreases. And it's only basically in the beginning of the 2020s that it would recover to the same level as before, or as before the financial crisis. But then the COVID crisis hit, and basically we only see a mild recovery, so in the following years. So you see that even if normally we are not interested in, or we are only interested in business cycle analysis for the FredQD data set, I mean, the specification we have here and the procedure we propose here can be applied to obtain additional insights reflected by these data sets. Just to go to the time varying specification, so the
Sylvia, we might need to get to a close actually.
Okay, so but let me finish just with this graph. So if you have the compound, you go to the compound time varying drift, you see that in both data sets you have some time variation. The factors itself and the interpretations do not change a lot. That's the baseline. Yes, so and basically that's it. So I will have the summary is here, and of course we have many additional let's say analysis and extensions that are lying. Thank you very much.
That's great. Thanks, Sylvia.